So this is how we define best fit. It's going to be the line that kind of cuts through the data and also happens to minimize this measure of mistake, this sum of squared errors. Now, what I want to do is jump over to our Excel sheet. So this will be our week 13, day 1 Excel workbook. We'll be on our first sheet, and I'm going to use this to kind of review a little bit of what we covered last week, and we'll talk a little bit about how to actually compute these squared errors. We won't be doing a lot of this in practice, but it is a nice review for some of the techniques that we'll see on future exams. Okay, so here we are in our week 13, day 1 Excel workbook. We're in example 1. And a couple of things that I want to review from last time. First of all, we have two different data points. We've got X, we've got Y. One thing that we can do is kind of visualize this data by selecting. Remember, you can use your Control Shift and down to select columns. We can go to Insert, and remember, we can insert a scatter plot. And we can get a nice picture of these two continuous variables represented as a scatter plot. Now, just by looking at the scatter plot, we can convince ourselves that it does seem like these dots have a linear relationship, right? They're following a line, and it seems like it's a pretty strong linear relationship. They're following it relatively closely. In other words, this doesn't really look like a cloud of dots. It looks like there's some variation from this magical line cutting through the middle. Now we can quantify this much better by computing our Pearson correlation coefficient. So that's what we're going to do next. And just as a little review, we use our Pearson command on the data that's been provided. So we're going to pick our first column, which is B3 out to B63. So that would be our X variable. And then C3 out to C63 is our Y variable. And this is automatically going to compute our Pearson correlation coefficient. And we can see that not only is it, first of all, positive, which reflects the fact that the line that these dots are following is upward sloping. It's also very close in magnitude to 1, which means that the correlation coefficient's fairly strong. This correlation is fairly strong. If we want sort of a measure of strength that doesn't depend on direction, right, negative versus positive correlation, remember we can compute our squared value just by squaring our Pearson correlation coefficient. And in this case, we get a 0.93. This is very close to 1. And again, the R squared, the closer this thing is to 1, the stronger the linear relationship between the two variables. Now what I'd like to do is figure out what's the sum of squared errors. So if we have a trend line cutting through the middle, and let me remind you how to add the trend line. If you click onto your chart and go to Chart Design, go up to Add Chart Element, Trend Line. And in this case, I want you to go to More Trend Line Options because I actually want to put the equation in the R squared value for this regression right on the chart. After hitting more chart options, we can scroll all the way to the bottom, hit Display Equation on Chart, Display R squared on the chart. So I like to see these generally. So usually if I have you do one of these linear regressions, I'm going to have you plot these. Okay. You can see that the R squared value matches up, 0.9302, they rounded. And you can see kind of in the background the regression line. Under here, if you want to, sometimes I like to make this a little bit more visible. I like to first of all make it a solid line, and then I typically just change the color so that it's easier to kind of see. You can also change the width of this if you want to make it a little thicker. So there's my regression lines cutting through the middle, and I want to compute my sum of squared errors. Now there's two ways to get the intercept and the slope. One is after you add the trend line, you can just read them off. The other is to use the intercept and slope commands. Notice here that it prompts you for the known y's first. So we have to make sure that we put our vertical axis, our y variable, our dependent variable, our response, however you want to describe this. We have to put our y-axis information first, 63, sorry, and then we put our x. So it's very important the order here. You'll get the wrong intercept value if you switch the order here. And we can do the same command. You'll notice this is matching up 11.58, 11.58. We can do the same thing with the slope command, putting in our y variable first, and then the x variable, our independent or predictor variable. All right, and we'll notice we'll get the same slope. Okay, so just as a quick review, how did we get these things? Well, we essentially looked at the height of our prediction, which we get by plugging in a certain x value into the line, and then looking at the difference between the actual y value and the predicted y value based on the linear regression. So this y hat value, I'm just going to insert a comment here. Compute y hat for this row by taking, essentially just, we're going to use this equation of the line, the 1.9537 times the x value plus 11.584. And what this is going to do is it's going to give you the height associated to these little green lines, right? Here's the x value in the row. We plug it into the line and it gives you the new height. So it gives you what we call our y hat values. And these, again, these are predictions based on the input, the predictor, the independent variable. It's a prediction for what our y value is according to this linear regression line. So here's how I'm going to do it so we can use our fill down formulas. We can grab x, and we want to multiply x by our slope. Now I want to make sure that this cell doesn't update, so remember you have to fix it using your dollar signs. To that, we're going to add the intercept, which also should not update, so we'll put our dollar signs in. And this will give me a prediction that's relatively close to the y, but not exactly equal. And I can fill this prediction down, and I now have little prediction y values for each one of the observations that go row by row. In other words, I now know the y value, or where on the y-axis each one of these green dots sits. Now, the next thing I want to do is compute the error. So these are my residuals, or my E sub 1s, E sub 2s, right? Each, the 1, the 2, the 3, the 4, these are all organized by rows. So this would be the error for the first row observation, error for the second row observation, etc. So the error I'm just going to define. So the error, or the residual, is going to be defined as the actual y minus the y hat prediction. Okay? And this we can do very simply with a just with a fill down formula. We have our actual y value here. We want to subtract off the predicted value, y hat. So here we can notice that there's an error of a negative 2.07 because my prediction is actually larger than the actual value. And now if I fill this down, I'll get these prediction errors or residuals for each one of my observations, for each one of my rows. And you'll notice again that some of these are positive, some of these are negative. And it turns out, by virtue of the way that this best fit line actually works, if you sum up just the errors, you're going to get 0. So obviously, as a metric for how well does this line fit the data, we don't want to do just the sum of the errors. So we want to get rid of their sign. And so what we're going to do is take each one of these things and square it away. Sorry, that was hard to see. We're going to take each one of these and square the error. And this is going, just like we did for the variances, this gets rid of the positive negative problem that we've been working with. And again, we can fill this down. So now when the error is big, like here we have a mistake of, right here we have a mistake of, we're off by almost 8 points, right? The error squared also ends up being big. When the error is small, the error squared ends up being small. So in a sense, you know, getting a sense for the fit, we can kind of add up these error squares, and it'll tell us more or less how well this line is fitting the data, or at least we can use it as a comparison for other lines. Now, we already know that this is the best fit line, so this will be the smallest possible sum of squared errors that we could obtain by using a line to model these dots. So finally, to get the sum of the squared errors, we just want to add all of these things together. So we're going to add from F3 to F63. Oops, that's 52. 63. And this would give us our sum of squared errors for this particular linear regression.